think you can, you are now able to share your screen.
Yeah, I do have that off. Is it visible?
Yeah. It's, your screen now is visible.
Okay.
So let me introduce Nilesh first formally. So Nilesh Kumar is a doctoral student in Technical University of Munich, and his field of interest meets with quantum algorithm, quantum computation, and applications. And today he's going to talk on quantum blockchain based on dimensional lifting generalized Gram-Smith crossover. So stage is yours, Nilesh.
Actually, I would like to correct you because first of all, I'm Kumar Nilesh. I try to mail QIQT also that I'm going to talk about something else.
Okay.
So
okay.
I hope it's not a big
Sorry
problem.
for the inconvenient. Actually, we haven't have the information actually get it. So sorry.
Okay, I mailed you, but it's fine. I hope changing of topic is not a big problem for you guys. But anyway, like I'm going to talk about quantum puff. And before I start, am I audible properly?
Yeah,
do I need to change something?
you are forward. Yeah.
Okay. Should I start?
Yeah, you can start.
Okay. Yeah, because we have already lost 8 minutes of it. Okay, so yeah, let's start then. So hi everyone, I'm Kumar Nilesh. So in this short talk, I will try to describe or motivate you towards a relatively new topic of quantum tokens. Previously, I have worked on quantum tokens, but this is a new direction of quantum tokens that's particularly called as quantum puffs. So my main goal is to serve this as an example of how we can provide a mathematical description of a hardware device through some information theoretic assumptions, and then we can use basic information theoretic tools to calculate various cryptographic quantities such as secrecy, secret key rate, and all other things. So one of the main application of any token is for authentication. So let's first see what is an authentication. So in simple term, it can be described as am I who I am claimed to be? So it's the major task in both classical and quantum cryptography. To achieve secure communication between any two party, Alice and Bob, it's necessary, like it's important to ensure that there's no third party intruder who is pretending to be the one of the legitimate party, like he's not trying to be Alice or Bob. For example, in QKD, we know that this is taken as an assumption. This is considered to be something that is already given. And some common means of authentications are passwords, biometrics like fingerprints or iris scans for humans. And similarly, we have PUFs. It's called physically unclonable functions for devices, hardware devices. How do we authenticate them? So first, let's look at what exactly a PUF is. It's called physically unclonable function. That does not mean it's a mathematical function. It's a hardware device. So in simple term, it can be described with an assumption that is that it is almost impossible to clone, even for the manufacturer of the device. So PUFs are devices that use uncontrollable random disorders which occur during their manufacturing process. So this thing that is random and uncontrollable serves as a tool for the security. So this disorder makes them hard to clone for practical purposes. For our application, the behavior of a PUF can be characterized by a set of challenge response pairs which are extracted through physically measuring or querying a PUF and measuring to get its responses. Now, due to inherent uncontrollable randomness, a PUF, it is hard to predict what will be the response given a particular challenge. There's no function that can describe this mapping between challenges and response. I mean, the function is usually very difficult to obtain. So even the manufacturer who manufactures the device cannot predict what will be the response given a particular challenge, or given a particular measurement, what will be the output. So this process makes PUF different from any other hardware tokens, in the sense that the manufacturer of other hardware token is completely aware of the behavior of the token that they have built. These are the picture below serves as two examples for classical PUFs. The first one is optical PUF in the bottom left. You might have heard of Samsung Galaxy phone where they have used optical PUF. And the second one is ring oscillator PUF. So let's see how PUF works in a very simplified form. Okay, let's mention. So I mentioned it that it's based on challenge response pair. You query the device with some challenges and you obtain a response as a result. So based on these data, you authenticate the device. Now, if you have studied the Bell inequality test like CHSS, you could see a similarity between these and that. So however, here we are not calculating any difficult mathematical quantities, but we are just verifying the response that we get based on a database that we already have. At least for the classical case, we keep a database. And if the response matches our database, then we accept it. And if it does not, we reject it. This is the simple form. So there are some basic requirements that a PUF needs to satisfy. Otherwise, we cannot consider it to be secure. First, we'll begin with the classical model, of course. Then later on, we'll try to generalize it with other requirements in the quantum case. They are very identical, but mostly the notation will change. So the first requirement is uniqueness. It simply means that two different PUF devices, when provided with the same input challenge, then their outputs should be different. That is, we can easily distinguish between any two different physical devices. The next requirement is collision resistance. It simply means that on a same device, if you measure it with two different challenges, the responses should be different in order to have unique pair of challenge response. We don't want two challenges to give the same response. So different challenges, different response. And the third requirement is kind of similar, but it's like same challenge, same response. So it's robustness, which means that every time same PUF is measured with same challenge, it should give same response. Okay, so now let's come back to the simplified authentication protocol with PUF and explore it more mathematically. So first, for a classical PUF, we have a database that which stores all the challenge response pair. During the manufacturing process, we have created a database where we created a device and we apply a challenge and we get a response, and both can be considered to be classical, and all those are stored in the database. And note, for the classical purpose, at least the database should be kept secret because it contains all the keys, all the challenge response pair that later on we will use to authenticate the device. I mean, once you query using a particular challenge, then that particular challenge response pair will obviously become public, but rest of them should be kept secret. Again, we are considering a very simplified case. So here, the first step is to you provide an ID to the device that you are considering. And with enrollment key x to power n, it considered it as a challenge that I mentioned earlier. Then PUF evaluates it based on enrollment function, which here I've denoted with f. Then you store it in the database. Then later on, when you want to authenticate the device, you put on the same ID. You put some challenge y to power n, and you perform the evaluation with the device. And then you match if the outputs are same, if the output matches with the database or not. Now, the problem is that puffs are very susceptible to environment as they are manufactured with random and uncontrollable effects. So even a slight change in the environment can cause the internal puff algorithm to vary a lot. So they're not, therefore we need some sort of error correction in it. I won't go into the detail of error correction because you can use any kind of error correcting tool that can be applied for this particular algorithm. But in short, we can do it with some sort of helper data that I've denoted with M. So this helper data will be stored publicly. And here at the bottom left, I have given some like mathematical description how outputs secret key K and helper data M is generated with the help of evaluation function E or encryption function. Then later on with the decryption function, when you provide the input Y to power N and corresponding helper data, which is publicly stored, you get estimate of K. So the main question is the estimate of K equal to K or they are not for authentication purpose? Now, there are some assumptions to the devices, whether it's classical or quantum. These the assumption that the equation that I have mentioned will remain the same. Only the notations will change. So, I have mentioned a lot of. I mentioned that it's a device, it's a hardware device. But when you want to evaluate its security, you need a mathematical model. So how do we model any particular physically unclonable devices? So we set on some security assumption that it should satisfy in order to have its reliability and security. 3 requirements I've already mentioned. And through these equations, we have translated those requirements in the form of mathematical way. So the first equation is here about reliability. The second one says that helper message that we generated for error correction is independent of the secret key. You don't want a public message to reveal your secret key. The third one is secret uniformity. This one is again important for machine learning attacks because machine learning attacks are pretty common in these kind of devices. Then the fourth one is that it gives you about the secret key rate R, and the fifth one bounds the privacy leakage from the helper message about the original data. So the goal is to find a trade-off between the privacy leakage and secret key rate. I won't go into the results because this is a short presentation, but let's look at how we can define a quantum physically unclonable functions. So mathematically, we define a lambda, delta R, delta U, delta C quantum puff as a quantum device, which satisfies some basic requirements that we have seen for the classical case. So, okay, so any puff is considered, I'm considering puff to be a quantum channel. I will go into detail later on. So it is generated with the help of Q-channel algorithm, and then it is evaluated. Any challenge or any measurement can be considered to be evaluated with the function Q-eval. And T is something you can consider to be as like testing parameter. So the first requirement from a quantum puff is delta R robustness. It means that any Q puff generated with the help of Q-channel algorithm, and we evaluate it with 2 different input quantum states, say rho in and sigma in, which are delta R indistinguishable. That means we can not distinguish it. They are very close to each other with the parameter delta R, you can consider in simple term. Then if the inputs are delta R indistinguishable, then the output that is generated, that is rho out and sigma out, should also be indistinguishable. It's kind of the third requirement that we saw for the classical case. So the distinguishability and indistinguishability will be important here because unlike classical case, we don't have a perfect distinguishable state in the quantum case. And if we work with just the orthogonal states, then it would be equivalent to the classical case. Now, the next thing is the delta U uniqueness. First, I should mention that the PUF here, we are assuming, like I mentioned earlier, that PUF, I'm assuming it to be quantum channel. Now you can consider it to be quantum source as well, and you can show that quantum source and classical source are kind of equivalent. But for my purpose, I'm considering it to be a quantum channel. So I can provide some justification on why quantum channels are used, at least in my work, to represent quantum PUF in my model. The most interesting result that I've seen, I don't know if there's such a result in classical case, but in quantum, we have that quantum channels are all encompassing. That means any physical transformation, unitary, non-unitary, even density operators, or even like quantum measurements can also be viewed as a quantum channel. So everything we consider in quantum theory is it's just a quantum channel of some sort. So it's natural to assume quantum PUF to be represented by some kind of quantum channels, and it provides a mathematical base to evaluate its secrecy and other information theoretic parameters. So this requirement basically says that two different quantum PUFs, that is, we are taking two different quantum devices, which are represented through two different quantum channels, lambda I and lambda j. They should be at least delta U distinguishable. That means we can distinguish between two different quantum devices with overwhelming probability. Note that this is not like traditional fidelity or trace norm. This is diamond norm, as we are dealing with quantum channels. Now, the last condition is a delta C collision resistance. Again, if you consider a particular PUF when it is evaluated with two different quantum inputs, which are delta C distinguishable, that means we are taking two quantum inputs which are like significantly distinct from each other, then they should produce an output quantum state which should be significantly distinguishable from each other with overwhelming probability. So now, once we have formalized the basic requirements and definitions of a quantum PUF, we can start analyzing various cryptographic quantities. I mean, we have already seen this slide. The basic requirements for secrecy will remain the same. Only you can change some of the notation in order for the quantum devices. But yeah, those are not my goal to prove any results here, but to provide you the basic motivation on how we can mathematically formulate a hardware device that is completely dependent on the manufacturing process, which are not built on some mathematical assumption, but so how we can mathematically describe its working, so that we can use information theoretic tools to analyze its secrecy and any other quantity that we want to calculate over it. And since it's almost time, so I'll finish here. And these are some references that I've used to describe the model. But yeah, so if you have any questions regarding it, you can ask now. Thank you.
Thank you, Nilesh, for this wonderful talk. Now the session is open for the questions. So I would request participants to unmute themselves and go ahead with the questions.
Thank you for your talk. I have one clarification. This PUFs, first time I hear quantum PUFs. So is it like new term which was introduced recently, or?
Hi, I think you're Ranjit or someone else?
Yes, Ranjit.
Hi, Ranjit. So PUFs are, in general, is a new topic. It was introduced in 2011 or something. I don't remember exactly, but not long ago. And quantum puffs is again relatively new thing. Yeah, it's a very new thing. We don't have much results on quantum puff yet. And the thing
What
is,
kind
like,
of
it's a hard.
benefits?
Okay, yeah.
Sorry.
No.
Please continue.
So,
I think you wanted to say something.
no, you can ask questions. So you're asking what some benefits of puff? Or?
Yes, because this is new to me, at least.
Oh, yeah.
Terminology.
You know QKD in quantum, where we used to communicate secret key. Now there's a basic assumption that the communication is happening between two authenticated parties, but it never says anything about how do we authenticate other party. So if you have a device, how do you authenticate that it's the right device for you? Again, like Puff is a tool that can be used in various processes. For example, it can be a replacement for QKD also because it has the ability to generate secret key. But the problem is you have to first identify that the device is not altered with by any third person or completely replaced by any third person. So this is the main thing about Puff, that it can authenticate the device. Further, like some of the quantum tokens can also do, but it has other advantage that even the manufacturer of the device cannot predict the challenge response pair. So it's independent of the manufacturer. There are some classical puffs for which manufacturer can manipulate it, but there are certain classical puff example for which it is also independent of the manufacturer, that even the manufacturer cannot alter it.
Thank you. So regarding quantum puffs, I can read these references or quickly
Yeah, you can
find
read
more.
these references, or you can just search it. There are not a lot of materials regarding quantum puffs.
Okay.
And sorry again for the inconvenience from our side.
It's fine. I just wanted to let you know here because I guess the mail, you might have missed the mail.
Yes. That's the thing.
Thank you for the invitation.
Okay. Bye. So our next speaker is Dr.